used for making my microfluidics. Yeah.
So SU8 is a
It's a photoresist. It's
yes.
epoxy resin based photoresist that it's hardened and cross-linked by photoactivation by UV light.
All right.
It then needs to be heated to release a photoacid, which then cross-links the compound, leaving the structures that you expose to UV light behind and allowing the unexposed material to be removed by the developing solution.
All right. So do you think it looks like they have SU8 in their final structure?
Quite possibly.
So you think they cured with UV?
Yeah.
To hardening?
I think they probably cure it with UV and then hard bake it.
Hard bake it, right? And you know the refractive index of SU8?
Not off the top of my head. I would say it's somewhere around 1.4, but I'm not sure.
Yeah, I guess it should be similar to silica or other polymer resist. Yeah. So 1.3, 1.4,
yeah,
or maximum 1.5. I don't know why they use SU8. There are many other things they can use. So amorphous silicon, that's what they're saying. On fused silica.
Maybe they use SU8 so that it's not quite refractive index matched to provide a phase contrast, which would enable the focusing that they're looking for.
Yeah. How do you think they made the amorphous silicon, the structure?
I would suggest that they probably used HSQ and did electron beam lithography to generate fused silica.
No, silicon.
Sorry, amorphous silicon.
Yeah, so silicon, the refractive index of silicon is about 3.4 or something.
Yeah.
So I think they give silicon to make the high index structure.
Yeah.
And they put SU8 to make a low index background, low index surrounding. Maybe they did RIE or I don't know. I think.
Yeah, I can see that doing RIE would work.
Yeah.
Or they could do maybe a
PECVD?
That's the word I was looking for, PECVD. Plasma-assisted chemical and vapor deposition.
I think the one thing is, it looks like the top layer should be very smooth. That means they so it shouldn't make a bump on top of silicon.
It's possible that they made the top layer first and deposited the silicon into it.
Really?
It's possible.
All right, yeah. We're kind of guessing at the fabrication.
Because in order to get a conformal coating with SU8 on a complex structure, it would be very difficult because SU8 is quite a viscous material.
All right, yeah.
So it would be less likely to fill all of the gaps and form a smooth layer. So I think it would be easier to fabricate by photostructuring the SU8 layer and then depositing material into that and then transferring it to the fused silica substrate.
Yeah, then how do you remove the rest of the silicon that deposit on the other places?
Good question. Maybe they've done it with a combination of other resists.
Yeah.
I don't know. Or maybe they've just put a very thick layer of SU8 over the top of their device.
Yeah,
And-
maybe it doesn't really matter that they have some little bump,
Yeah.
on that. Right, yeah.
Because
We-
if the SU8 layer is several tens of times larger than the silicon layer,
Yeah, then it
The
wouldn't
bumps
do
will-
much, yeah.
propagate out.
Yeah.
And you can probably rely on the self-leveling of the SU8.
So this is one of the metasurface. It doesn't look it's two combined. So
Do you think it's Metasurface 1 or Metasurface 2?
yeah, that's the question. I don't know. I guess it's two. I don't know which one is more. All right, let's go to the figure. Oh yeah, what's that?
They flipped it upside down and put gold on it.
All right. So they have gold on it. That means this is metasurface 2,
Yes.
right? So because yeah, it will reflect back.
Yeah.
And
So-
they're going to combine metasurface 1 on top, I guess. Or
I think the amorphous silicon layer is your Metasurface 1.
really.
I think.
And where's metasurface 2?
Well, I think Metasurface 2 is the gold film,
Really?
but I'm not sure. Maybe this is just how they make Metasurface 1 or 2.
I think it's metasurface 2, and they have metasurface 1 somewhere else.
Okay.
This, what is that?
That's the fused silica.
So yeah, this green thing was fused silica. So right, the green thing is fused silica, and the gray thing is SU8.
And the red is the...
Red is amorphous silicon.
Yeah.
And what's that?
So it's showing the transmission properties of that film as a function of the diameter
Yeah.
of the fused... of the silica. Amorphous silicon, sorry. Of the
Yeah,
amorphous
yeah.
silicon.
Sure. So I guess they fixed the thickness, I mean the height of the silicon.
And change the diameter
change
of
the
the
diameter.
rods.
And I don't know about the pitch or period of the array. Maybe they fixed.
It doesn't seem
It doesn't
to
say,
indicate.
but yeah. But they're not measuring based, obviously, not on one rod, but they have an array of a rod. So blue line is transmittance, and the green line is the phase over 2 pi. Right?
Yeah.
I don't know what we can get from here.
I think this is just showing the behavior of the surface and saying that as the diameter increases, the phase shift increases.
Yeah. But the thing indicated by the gray region is showing that transmittance is very low in those diameters.
Yes.
And those are where the phase is decreasing by diameter.
I think that the phase is discontinuous at that point.
Yes.
There seems to be a significant phase jump at that specific diameter.
Yeah, well, as the phase increases, and at that point it decrease and increase again.
Yeah.
And decrease and increase
again.
Yeah. So there's a, well, the phase has a negative slope. But in terms of diameter, that I don't know what.
It could indicate that there's absorption resonances in the silica.
Silicon?
Sorry, silicon. Yes, not the silica. Silicon.
Yeah. Did they fix their wavelengths? I guess, right?
Yeah, they would have.
Yeah. So somewhere invisible, like 600, 700 or something.
It's probably mentioned in the caption.
Yeah.
We'll get to it.
Alright,
but I would suggest maybe what's happening there is you get at a particular angle, you may excite a resonance in the structure because the momentum of, oh no, this isn't angle, is it? It's just diameter.
Yeah, and it's normal instance.
So maybe at a particular diameter, you excite resonances in the. If those were equally spaced,
right.
I would say it was a harmonic resonance in the silicon, but I don't know. Let's find out what they say.
Yeah, all right. So it was a transmittance.
Oh, Daddy. Hey.
Sorry. Let's see reflectance.
Oh, okay. So one of those peaks is explained now.
How? I don't know.
Well, does the diameter there match?
All right. This is 225.
Yep.
I assume that's 225. All right. Yeah.
So one of them is explained by the
Little
reflectance, but the other ones.
Upon a time, there was
How was explained? Well, that was the. Interesting.
Because at that wavelength, the.
Well, they measure the reflectance.
Yeah.
By putting the gold on bottom. Did you recognize it?
I see.
And this is from the other side. So the light before the transmission, the light was coming from the SU8.
Yeah.
But this one, the light is coming from the fused silica.
Okay, so it's not explained at all. That's really interesting then, because why is the second peak missing? The second absorption peak.
I mean, because I was a bit confused that if it's the same structure, if the transmittance is 1, the reflectance should be 0. But that doesn't make sense. So, but here reflectance is 1. So, all right, something's different. Yeah. Yeah, and all right. So, but again, yeah, it's showing there's something weird in the same diameter.
Yeah, but it's interesting that the higher diameter is not showing any influence in this case.
To 60.
Yeah.
It's not showing anything. All right. Yeah. Interesting. So if it's absorption, if it's due to the absorption of the silicon rod, then it should show something at 260, right?
Yeah.
As well.
So what that probably suggests then is that the one at 225 is due to absorption by the silicon rods, and the one at 260 is due to reflection by the silicon rods. Because in the reflection mode, if it reflects off the silicon rod, you see no difference. But in the case of absorption, you will see.
Yeah, well, there are basically 2 ways to lose the light if you measure the transmission. The one is reflection and the other is absorption. So this one is explained by absorption.
Yeah.
Because it's lost in transmittance and reflectance at the same time.
Yeah.
But this one was lost only in the transmission. But reflection is fully reflected. So that's reflected.
That's reflected by the silicon rods.
Interesting.
But it seems that the absorption one is, so the one at 225, it's only partially absorbed. Most of it is still reflected. Because if you look at the reflectance here, the reflectance only drops to about 0.8.
Shouldn't it, if it's absorption, shouldn't it absorb more in the reflectance measurement than transmittance measurement, because it experienced twice?
That's actually what I just said.
Yeah. So yeah, that's how I understood what you said.
Yeah. So what it's showing is that at 225 you're getting some absorption.
Yep.
But it's also being reflected.
Right.
Yeah.
So it's absorbed and a lot reflected. Now here, right, reflected are measured here. So, right, yeah. So maybe this 225, I guess, is related to the wavelength.
What?
Everything.
What one?
Because it's a diameter of the
What one, Daddy?
silicon.
What one?
This one, this gray thing.
I would say so, yeah.
Yeah, so it's a resonant mode of the
What
related
one?
to the resonance of that particular wavelength.
Yeah,
What one?
it is interesting though, because in the abstract they said that the light, the object acts as a retroreflector in the near infrared.
Oh, near infrared.
I think that's what they said. Or was that when we were reading the 2 by phase shift from the other article?
Oh, we just quickly. Maybe we can go back to the abstract. Yeah, let's check that out. It doesn't say near infrared. Oh yeah, near infrared.
Yeah, it is near infrared retroreflector. So that should be significantly different from 225. But I would suggest that maybe it's 1/4 of the wavelength. Because infrared goes from about 860 to about 1.2, 1.3 micron.
Yeah, usually silicon has absorption up to something like 1 micron or 1.1 micron. Then from there, silicon, well, obviously at 1.5 microns, it doesn't have absorption. Well, maybe it has very tiny little bit, but yeah. Basically, we think it's transparent for 1.5 micron. So that near infrared, I don't know what's the exact wavelength, but if it's by absorption, then means somewhere around 1 micron, I guess. I don't know. Right, where are we? So you want to read the caption?
Sure.
All right. You can have this mouse.
Okay. Transmissive and reflective metasurfaces forming the retroreflector. So component A shows a schematic illustration of the transmissive metasurface design used to implement Metasurface 1. So this design is Metasurface 1.
Oh, really?
Yeah.
All right, yeah. That's wrong.
Okay. And then B is similar to A, but for the reflective metasurface design used to realize Metasurface 2.
All right. I was right. I don't know. I was wrong or right. Yeah, I would just say I was right. Yeah.
The reflective metasurface is similar to the transmissive one, except for an additional gold layer deposited over the SU8 cladding.
Yeah.
C is the simulated transmittance. It's not actually measured.
Oh, I see. That's why it's so smooth.
Yeah.
Yeah, I would recommend.
And transmission and phase as a function of nanopost diameter for the transmissive metasurface shown in A. For D, the simulated reflectance and reflection phase as a
So
function
their
of
structure are
nanopost
different.
diameter.
No, they're not different. Yeah, but just
Yeah. Well, no, they're not different. They just have the gold reflector.
right. Yeah.
The nanopost diameters corresponding to low transmittance in C or reflectance in D, which are highlighted by grey rectangles, are excluded from the designs.
All right, they excluded. All right.
The nanoposts are 600 nanometers tall, the lattice constant is 450 nanometers, and the simulation wavelength is 850 nanometers.
Yeah.
So,
See method for simulation videos.
Yeah.
Yeah. So I assume that if it goes higher than, longer than 1 micron or significantly longer than 1 micron, then it doesn't experience any absorption. So I expected some wavelengths around there. Yeah. 850. That's fairly close to the visual one. Yeah.
okay.
Good. What else we still don't know?
Well, I'm still not sure whether this is indicating metasurface 1 and metasurface 2, or whether it's indicating metasurface. So, sorry, the question I'm asking is metasurface 2 just metasurface 1 with a gold reflector?
I think so.
Then I'd be really interested to understand how the mathematical transforms that are being performed can be so different.
Well, I would say they have same unit cell structure based on the SU8 and silicon nanopost, but they vary the diameter of nanopost. So designed differently. So for example, here they can change the phase from 0 to 2 pi.
Yeah.
But they excluded this part to design. But anyway, they can fairly broad range of phase change here. And for the reflection as well, they can change from 0 to should be 1 in this sense. For the red graph, it should be 1, I think. Yeah, but anyway, yeah. So they can choose different diameter to make different phase change.
Yeah. So I guess then the way that works is that in metasurface 1, they pattern the positioning of the rods so that depending on the incident angle, the phase the momentum transfer results in focusing to different locations on metasurface 2 to provide different momentum transfer on the reflected light, so that it can match the incident angle, the angle the light's coming in. Well, an angle is like this, the gap between my hands, and I'm changing it 90 degrees, 45 degrees,
And maybe
0 degrees.
this. How about this?
That's very
That might
close
be-
to 0.
Could be 1, 2,
This that one?
maybe that's 0.5. I don't know.
All right. So near infrared, how much was it? There was
It was 850.
850. well, in the simulation at least. And what is the lattice constant?
459.
Was 450?
Sorry.
I think so, yeah.
Yeah, nanometers.
And the height
600.
of nanopulse 600. What else? What number was there? They're all right. And I think
The lava one.
I'm sorry, that was me. Yep, that's all the numbers.
평아 이거 태블릿 잘 챙겨. 태블릿 잘 챙겨. Yeah, 이거 뒤에다 놓을게. Well,
I put it in a bag.
I think